Hello, everybody. It's great to be here with you today, and I'm so grateful to be part of the Society for Scientific Exploration conference again. It's probably 12 years ago when I first walked in the room and met many of you. I'm going to talk about space-time holism. I have a master's in physics and two books, Living in Flow, The Science of Synchronicity and How Your Choices Shape Your World, and Leap to Wholeness, how the world is programmed to help us grow, heal, and adapt. And especially the second book, both the books are really based on the research that I've done, trying to understand synchronicity, trying to form some as a physicist, some description of synchronicity. And the latest paper is really has been my target for many years. I'm going to share it with you today. It's a formulation of quantum mechanics through the lens of Fourier transforms and holograms. And as such, I think it's a step forward on our understanding of time specifically. Time in physics is a sort of a stepchild that hasn't been really fully realized in our descriptions. And I think we need to understand it as holistic. And this actually helps us move forward in our descriptions of many other things in physics. So we'll cover today a derivation of holistic time, a rederivation of the principle of quantum superposition using holograms. And we'll mention synchronicity as sort of the potential future research or connection that we can make. And then after this session, we've got a break and I've booked a self-organized room to talk more about synchronicity as a collective, just an open conversation about synchronicity based on what we talk about here. So all of you are welcome to join and stay in this room for that. Myself, I was already introduced. I did this research through the Fagin Foundation and the Foundational Questions Institute. Those are the funding agencies, and the research was done at the Tice Research. The paper is available for open access. It's called Spacetime Paths as a Whole, published in Quantum Reports this past winter. So why is this research important? Well, as I mentioned, time is not fully realized in the physics formalisms. We get closer to it when we make our equations Lorentz invariant according to special relativity, but there are still things like the time ordering operator and things that sort of stand out as ways we impose causality on systems that sort of bother me. And in particular, the main one is that if I could summarize quantum mechanics, it's a relationship between position and momentum. And that relationship is the Fourier transform. And there is a similar relationship between time and frequency, but it's not leveraged as much. They're not leveraged equally. For instance, when we study crystals, we often work in the alternate space, in the momentum space to describe crystals, because it's very useful, it's very practical, but we don't do that with time and frequency that much. So there's some differences in the way that we perceive time, and I think it has to do with our personal experience of time, right? We think of time very personally. We live in the present moment, and that's what we bias the present in favor of the present over the past and the future. And this notion that we're at a particular point in time, we think of time like a grain of sand, a single grain of sand, and we're going to talk about it in different terms today. Rather than a grain of sand, we're going to talk about a line of time. So just a little background on time. In doing my research, I did learn about some other notions of time from other cultures. The Aboriginals, for instance, in Western Australia, think of life like a dream, the dreaming. And we're experiencing a dream, and the past continues to exist in the present. And the future is here too. So there's this eternity or eternalness to time versus, it's very hard to understand that when you're in the Western view, which is that we're on a line moving forward, point by point through time. But so I want to align what I'm researching here in moving forward in physics with these alternate ways of looking at time from other cultures. Hippocrates from the Greek culture identified chronos and kairos. Chronos is what we're used to, the linear passage of time. Kairos is a proper or opportune moment for a given action. So kairos is really helpful for discussing synchronicity, where you go to the airport and you walk into the gate and there's somebody there. And it's like if you had walked into the gate 10 minutes earlier or 10 minutes later, you might not have met that person. So the opportune moment to meet them is right when you happen to walk in. And that's what kairos is like. Kairos is qualitative time and chronos is quantitative time in a sense. So my proposal or way of looking at this is kind of like the following. Instead of life coming at you, like you're sitting there watching it happen, and it's a clock ticking in front of you, you're really on a path. You're on a timeline through the multiverse. And this is just a visualization of the many worlds branching wave function. Specifically, I've identified the touch points where you make decisions. Those are the flags. And that's where the multiverse branches. What we're going to speak about today is the time in between the touch points. Those are when you're moving along a path from a beginning point to an end point. And I'm going to show you mathematically that these paths are deterministic, they're unitary, and they exist as a whole. You can't divide them in half or take steps along them, but you are on a trajectory. And this element of being on a trajectory is really important, because as soon as you talk about time as a line or as a whole, you've got a beginning and an ending. You've got a plot, you've got a storyline in that timeline. So it brings into the narrative questions about meaning, and synchronicity fits really well in there. So I want to give a little background, educate those folks who are not familiar with the Fourier transform, and image processing is a really helpful way to understand this. So this is just a little background on the mathematics. In digital photography, you can have a photograph like the city here, and it's made of pixels on your screen. And there's a blue pixel in one position and a gray pixel in another position to indicate what it's representing. This is the territory. This is the real world. But there's also an equivalent representation that I call the map, which is called the frequency domain. And the frequency domain says, okay, we can decompose this city in terms of the patterns that make up the city. And by patterns, I mean like zebra stripes heading in different directions at different frequencies. And these patterns, when you put them all together, they give you the picture. It's amazing, but they do. And on the right, we have a map, which is essentially a recipe for how to do that. So every dot on the map corresponds to a different frequency space that you would draw on the territory. And when you put them together, you get the buildings. So let me show you how this works. If you have lines that are vertical and sort of spaced far apart, like in the first diagram, that would be a small frequency heading left and right. So you draw two dots slightly off the center, left and right. In the middle one, you have horizontal lines that are pretty high frequency, and those would be two dots pretty far from the origin in the vertical direction. And you can see the third one is just illustrating that they can go at an angle as well. So these two dots in the frequency domain, they tell you a lot. Just 2 points in the frequency domain fill up the entire spatial domain with information or with picture. So you can fill up all of space or affect all of space with just a point of information in frequency. So here's an example of two dots that I put on the map and the territory, how it's affected. It puts a frequency pattern on the screen with those two dots. And I can do that with more dots and get sort of an interference pattern, do it with more dots and get more interference. And I start to get really complicated shapes. And then you see the magic. You start to see that there's buildings there. There's actually something emerging from the patterns. And so this is the way that real shapes emerge from the interference of very complicated layout of the frequencies. And that's what the map does. It's a very specific recipe. It's not random, very specific to give you exactly the picture that you're looking at. And I can show you here how I can create out of pixels, I can create the city, but I can also create it out of lines. So by putting this is the same amount of data in each case, but it's just building the city in a different way. On the left, it's building it in terms of pixels, which is really familiar. That's what I would call reductionist, because every point in the picture corresponds to a different color pixel. But on the right, it's not reductionist, it's holistic, because it's being created from patterns which take up the whole screen. And these patterns come together to relate to each other and interact to give you the same image when you have enough of them. So consider that if I wanted to remove a building, I wanted to alter the picture in a very specific local way. On the left, it would be very easy. I just take a pair of scissors and cut around the building. Or I take a drawing tool and I erase those pixels. On the right, it's impossible. If I erase the frequencies corresponding to that create that building, they're also creating all the other buildings. So I erase any frequencies, I'm going to modify the entire picture with all the buildings. So there's no way to locally modify something when you build it from patterns. And this is why we call it holistic. There's a one-to-all relationship between these domains. Let me show you this one-to-all relationship even deeper. If I take the map and I filter out some of those frequencies, this is a low-pass filter. So I've blocked out the high frequencies. What I've done is I've blocked out all components that contribute to quick changes in color across the screen. And that means I'm blurring the edges. So now I have a blurry screen, a blurry territory. But I've made a local change to the map in the frequency domain and affected the entire territory at once, one to all. I can do a high pass filter as well, where I block out the middle frequencies. And what I get is an edge finder. This highlights the edges and removes sort of the DC component of the picture. So you can make these changes, which they do in Adobe Photoshop. Graphic designers are very familiar with this. In music, you also do this. This is how you do a graphic equalizer and change the high end or the low end of a sound. So that's a background on the Fourier transform and how it applies to signals in engineering. So now I'm going to take that background and start to apply it to the quantum formalism. Before I even do that, I'm going to talk about holograms. So a hologram is made in the following way. You shine light from a laser onto an object like the city, and you also shine it onto a mirror. And you interfere these beams on a piece of film. And the difference between the beams encodes the very specific, unique information about the city that you see. So in the film, you encode this unique but impossible to decipher pattern, and it's fixed on the film. And then when I shine light again on the film, it reproduces that pattern as if the city was there, and you appear to see a city in all its glory. So what's special about a hologram is that each angle of the observer is a unique perspective on the whole image. So right here, the hologram is the gray rectangle that you see in three places: left, middle, and right. And in it is this image appearing of the city. It sort of floats there. It's sort of ethereal. And you can tell I've put a star on a building in front and a circle on the building in back to illustrate the depth. And you can see that as I move my position from left to middle to right, the star and the circle move as if there's parallax, as if they're separate in space. And so there's this illusion of depth perception. And what's really crucial, this is sort of the key point, so I'm going to say it a couple times. There's two different definitions of space here. There's the position of the star and the buildings. Each building has a certain position associated with it. And then there's the position of the film. And these are different things, because when you move your perspective, the star and the buildings move across the film. So you need two sets of numbers to describe the position of the system. You need to describe the image itself, where it is, and then the film, where on the film you're looking. So there's a separation between the image and the film background itself. And this is going to come into play in a minute when we talk about actual physical events in space-time being like the image you see in the hologram, and the fields themselves being like the film that you can't actually see and observe. So just a quick note, if you look at this hologram from an angle, or if you cut part of it and look from the side, it's like looking through a window, like these curtains. You can look behind a place that you've cut to see what's there. So that's just an intuitive piece about the hologram. It's holistic in that sense. So I want to jump into the theory and how time can be represented in this way. So there are two postulates in my work, and these are sort of replacing the postulates of quantum mechanics, although this theory doesn't fully replace quantum mechanics, but just quantum wave functions, propagation. So in the first postulate, a system is fully described by four-dimensional signals in the space-time domain and the frequency domain, and these are related by the Fourier transform. So this is the wave function. Okay, it's a four-dimensional wave function, space and time, and it's got its frequency domain counterpart, which is also four-dimensional. And interaction is the second postulate. It's accomplished through convolution. This is just what happens when you filter a data signal. So what I'm doing is just formulating quantum wave functions as data signals. That's what this is doing. If you start from there, you get an equation on the bottom here, which is the fundamental equation of evolution. This is what I replaced the Schrodinger equation with. So to get to that, look at the image, the picture here. You've got light coming from the left, hitting a piece of film that's projecting. And so if you look at the top symbols, you've got G sub I is the original light. It strikes T sub A, and that turns into G sub T. It's a new signal. And so the signal G that propagates across the room to go to a screen is actually propagated with this letter capital H. Capital H is the amplitude transfer function, and it's operating in the frequency domain. So what we do to move a signal across space and time is we convert it to the frequency domain, and then we modify it there, and then we convert it back. That's what the lens is for, to convert it back to the spatial domain to get it to the screen. You can do the same thing with the wave function. The mathematics is exactly the same. Specifically when you treat the wave function as a four-dimensional x and t, or x, y, z, and t wave function. And I'm going to get to in a minute exactly why that's different from the Schrodinger equation wave function. But what we're doing is sticking really strictly to the math. Space and time are both just independent variables in this four-dimensional hologram. And the equation is essentially you start with the psi in the spatial domain, space-time domain on the right. We're looking at the bottom equation. You multiply by some function v of x of t, and this is essentially related to the potential of the system. And then you Fourier transform it. So you convert it to the frequency domain. You multiply it by another signal, which has to do with the kinetic portion of the Hamiltonian. And then you convert it back to, with the inverse Fourier transform, to psi prime. And that gives you this updated wave function. Now, just quickly, what's happening here is you're taking your signal, you're modifying the phases in a specific way to evolve it, and then you're converting it back to the space-time domain. Now, here's the key point. This whole thing is describing a system of space and time. It's a map of space and time, and therefore it cannot change in time, right? Because if something has time as its variable, the function itself cannot evolve in time because that's its independent variable. So psi, in this case, unlike the Schrodinger equation, psi cannot evolve. And what that means is you need the equation on the bottom, psi and psi prime have to be exactly the same, invariant. And what that means is v and h have to be specifically formulated so that they cancel. So that the change that happens from v in the spatial domain and then cancels with the change that happens in h in this frequency domain. And so when you get back to the inverse Fourier transform, you get back to the original function. So that's what I'm working with to get the mathematics of dynamics out of this system. This is not Schrodinger's wave function. It's, I think, a generalization of that. In the Schrodinger case, you have a 3D function evolving in time. And you can take a cross section or a time slice of that wave function, like the strobe light of the basketball here, or the quantum fields on the right, top right. You have these slices of time, each of which has a distribution of fields. But you can separate at every given time, there's a recognizable distribution. This is not true of the holographic wave function. It's truly a four-dimensional interference pattern, and cross sections are meaningless, just like a hologram. If you take a hologram and you cut it down the middle and you look at the data right along the edge that you cut, it doesn't mean anything. It doesn't represent any position of the image or anything, because the image, like the city before, when we tilt, the city moves. It's not associated with a specific point on the film. So there's this separation between the film and the image, and that's what we're seeing here. What we're talking about in the wave function here is the film, the background film that gives rise to the dynamics of particles and events, and those are the image in the hologram. So just to give you a specific example of how this works, this is an abstract version. This is not true numbers, but if you have some kind of interference pattern that looks like this, time and space on the bottom left, but again, this is a hologram in both space and time. And that corresponds to some set of points or objects sitting in space above the hologram that it's encoding. So this hologram encodes a dynamics. It encodes a trajectory. That's what I'm trying to say. And this trajectory is like the slip and slide. You get on at one point at the top, you know exactly where you're going to end up at the bottom at some time later, because the hologram encodes the entire journey. And so our experience of moving along the slip and slide is a personal subjective experience. But the mathematics is pointing to an abstract, more objective, indefinite reality where the entire timeline is defined all at once. And the mathematics here in the free particle case is when you set the potential v equal to 0, you just get this function f, a Fourier transform of the wave function, times this phase factor e to the I kx naught minus omega t naught. This is the general equation of a wave. But you need to make, the whole constraint is to make the wave function invariant. You need kx naught minus omega t naught to be 0. And that's how we get, that constraint is how we get dynamics, because the equation kx minus omega t is the equation of a traveling wave or a particle traveling at a specific velocity. And so this is essentially Newton's third law, saying that a particle will stay in motion in a straight line in this case. So that's the idea. The space-time trajectory is created as a whole from this equation that you see in the top right. And this is important in the following way. If I take a distant starlight traveling to Earth for like 1 million years, and it hits Houston, Well, that trajectory is defined as a whole in the frequency domain from beginning to end. And that's a really key idea. And I've just drawn a sort of a picture of what that would look like. This is a sinc function, a dying sinusoid, corresponding to like a particle in a box, where you've got the light existed at one point, but not before that time. And it traveled and then it stopped existing when it got absorbed and not afterwards. So there's like a particle in the box where you've got a sharp beginning and a sharp ending. And that corresponds to some pattern in the frequency domain. Well, if I insert a satellite, I've got a different endpoint. And so the Fourier transform of this second example is fundamentally different. Every frequency is changed. There's not like part of it stays the same. So the journey before it hits the satellite is paradoxical, because I've now changed the pattern in the frequency domain according to which it was traveling, but I've modified it like after the fact. But the frequency domain doesn't have time in it. Time is removed from the frequency domain. And so this timelessness is really a conundrum. And the only way to resolve this issue, or the way that I resolve it, is by suggesting that there are both possible frequency patterns, both possible holograms that are possible. And it's not until the satellite comes into place that one of them becomes the one that the light's been traveling according to the whole time. So this is just reinforcing the notion of a many worlds or multiverse. But we didn't start with the traditional quantum mechanics. We started with the mathematics of Fourier transforms. And there's a key point, which is that the satellite now becomes an essential part of the system. It's just because it's a macroscopic object makes no difference here. It is part of what creates the frequency domain pattern, and part of what macroscopically is in a superposition on these different branches of the hologram. So from this holism comes the notion that macroscopic objects as a whole also have qualities, that they can be defined quantum mechanically, not from building them up from parts, but as a whole. And this is really different because the idea of decoherence is not an issue. You're not adding up the little atoms one at a time and having them decohere. You're talking about the quantum mechanical properties of an entire object, a symbolic object. So that's one of the, I think, most controversial pieces here. So just to emphasize a couple of points before we close, I want to clarify this idea of different types of descriptions of space and time. You've got the visible coordinates of the city, like this, that's what the star is. It's a thing you can measure. Oops, I went back. And it's what you see. And then there's the non-visible parameters, which is the film. And this is a distinction that's very important. It leads to this notion of relationality, that in this formalism, the quantum mechanics is required to be relational. You've got this separation between the film and the image that you're seeing. So timelessness is one of the corollaries here. The wave functions are unchanging. A smoothly evolving present doesn't exist. In the frequency domain, there is no such thing as time. So if the frequency domain is describing an entire path through spacetime, you can't single out a particular point on that path in the frequency domain. There's no such thing. So there can't be any physical reality or significance to that particular point on the path if it doesn't get represented in the frequency domain. So the idea of a present moment is a subjective idea, not an objective idea. We've also talked about holism. Frequency space defines paths through spacetime as a whole. Motion is encoded as a whole into the phase distribution. And relationality, the idea that only interactions are physically meaningful, only relationships, only the measurement I make is relative to me, and the results I get are relative to me. And so there's two different types of space-time, and this comes from the sense that the world is holographic in a real sense. It's really mirroring the mathematics of holograms. So novel conclusions here: quantum superposition emerges for systems as a whole, including macroscopic objects, and the world must be relational. And this is specifically targeting some of the interpretations of quantum mechanics which can be distinguished. It's a famous problem that you can't distinguish interpretations of quantum mechanics, but Penrose's gravitational model and the OR, orchestrated objective reduction, are not consistent with my proposal here, because they imply objective collapse. And this requires a relative sense in which the world is really informational and not objectively collapsing. So there's just some ability to distinguish experimentally between these views. We have 5 minutes. So I'm just going to hint at how this points to the possibility of synchronicity. So this leads to, because of the relational aspect here and the fact that only events are real, only the interactions are real. When light leaves the sun, that's an event. But it's not until you see it on Earth that another event happens. And in between, there's all these branches of possibility. So here's the layout of all the multiverse branches. When you see the light, it retroactively becomes the path that it traveled. And this is known as the delayed choice phenomenon. But in this theory, it applies to all scales of objects, macroscopic or microscopic. And so there's 8 minutes of undetermined time here that get retroactively filled in based on the observation that I make to see the light at the last minute. And this is similar in language. You can get a sense for what this means. I call it retroactive event determination. If you say the sentence, the old train, you probably picture a train like that. The old train left the station. So you're picturing a train moving out of the station. But if you change the end of the sentence, the old train the young, then you have a very different meaning. The elders are training the youth. The words in the beginning of the sentence change their meaning according to the end of the sentence. So this is called local ambiguity, and it's what makes possible synchronicity, in my view. A synchronicity, in my definition, is an unusual circumstance whose meaning becomes clear in the future. So it's not until later that there's a connection, and there's a connection across time that's possible with this notion of timelines. We have a tree drawn here, and you can see each of these tree branches is like one of those lines I drew earlier, this unitary evolution, and there's the branching points. And the future experiences at the top that we're seeking to have are what we call the apples, the target experiences. And in the middle are these events that happen to us, which we don't understand why they're happening, but they're happening because they're part of the storyline that leads to the apples at the top of the tree. So because there's this connection from past to present to future in a timeline, you can actually start to look at how these things interrelate atemporally, and that this is exactly what we need for synchronicity, I think. And so synchronicity is possible because of unobserved timelines, because of the nature of unobserved timelines and how they can fall into place in different ways based on the choices we make. And then that's something I'm speculating here that we can go beyond maybe in the follow-up room. But I think it's all supported by this notion of time as a line instead of as a dot. So, and takeaways are timelessness, holism, and relationality. And I'll skip the piece about quantum field theory, but if you're interested in the relationship to quantum field theory, we can talk about that. I'll just touch on Bohm's implicate order. Bohm sought to develop quantum mechanics into the implicate and explicate order, and his structure emerges naturally in this formalism. He's been a huge inspiration and motivation for me, his theories. And his favorite metaphor was the hologram and the Fourier transform. So that's what drew me to this. And here we've described the implicate order without space or time parameter, as one would expect for an implicate order. Yet a space-time explicate description can be obtained from the implicate description through the Fourier transform. So I think it's a very natural clue that the Fourier transform does all this, and I've tried to formulate it in the simplest possible way using the mathematics that we already know and love, and just apply that mathematics really purely to space, momentum, and to time and energy equally, and seeing what that tells us about the mathematics and the physics. So if you want to follow up on the paper, it's available through the MDPI website at Quantum Reports Journal. It's called Spacetime Paths as a Whole. If you want to read an interview that I just was part of recently on holographic simulation theory, you can go to the link there, thetinyurl.com. It's also on my website or on medium.com. And again, the research was supported by the Foundational Questions Institute via funding from the Fagin Foundation. Great folks to work with. I really am grateful for them. And I do have workshops that I lead on flow, synchronicity, and wholeness. So I have one coming up this weekend, in fact. You can just go to my website below to find out more about what I do and other research and my books that are there on the left if you'd like to reach me. And that's synchronicityinstitute.com, which is my organization. Thanks a lot to the SSE and the organizers this week. I really appreciate being here and appreciate all of your contributions. So I'm assuming we're out of time and we're going to do questions. I'd love to do Q&A, and I think there were some questions in the chat. So let me open that up.
Oh, of course. First of all, excellent presentation, Sky. It was something. It was something really. So there's some comments regarding that. Some part of your talk. It was a great metaphor. I think it was related to the holograms. There's a question here. So if your formulation is in some sense an improvement of regular quantum mechanics, of course, it would still agree with all the well-verified tests, right? Have you reproduced anything like the double slit or the hydrogen atom in this model?
The hydrogen atom is the best example. The hydrogen atom is a slightly different mathematics because it's radial. So you take this Fourier transform idea. The examples I do in the paper are tying it into basic systems with spin and with the simple harmonic oscillator, or the quantum harmonic oscillator, because those are some basic examples that are foundational. I do touch on the hydrogen atom. I don't work it out explicitly, but what you would do, instead of using the Fourier transform, you'd use the spherical harmonic transform, because what you're dealing with, the basis states are spherical harmonics, as we well know for hydrogen atom. So that's what's so beautiful. The mathematics that we see in the periodic table from the hydrogen atom, the states of energy, is exactly the clue for what basis state we're working with. And that's the transform that we're using here. So I haven't done that, but I feel pretty optimistic that that's one of the clues that led me on here. But you'd use a different transform for that. So, and one other point you do is that the potential, which is essentially a filter that you apply in the space-time domain, that's the way the potential comes up. That would be the Coulomb potential for the hydrogen atom. And that's why you need those spherical harmonic transforms, because that's a Coulomb potential is in a radial coordinate system. And then you work out the same mathematics where the phases have to vanish. And then you get supposedly, theoretically, you would get the constraints on the quantum numbers that you get for the hydrogen atom.
Super interesting stuff. So there's another comment / question regarding a part of your presentation that reminds of various Lagrangian approaches, and also Cohen and Elitzur as well, sort of a mashup of those theories. Can you elaborate? Can you comment on that one?
Yeah, so very much Lagrangian. Lagrangian is a timeless representation, sort of a timeless theory, because you're dealing with the whole path and then calculating what's the action associated with that path, and then calculating the action associated with a different path. One of the main calculations I do in the paper, which is not original, is showing that how you essentially get from the path integral formulation, which is generally formulated in terms of the Lagrangian exponential and the action, minimizing the action, how you get from that to essentially a recursive Fourier transform. So when you time slice, in the Lagrangian formulation, you don't time slice. You look at the whole path and all these different possible paths, you weigh them according to the action, and then you find what's your classical path or whatever. But if you time slice that, what you're doing is essentially observing the system at every time. You're enforcing an order in time by that mathematical structure. And what that does is it takes the path integral and it turns it into a inverse forward, inverse forward, inverse forward, inverse Fourier transform. So this recursiveness of the Fourier transform is what the experience we have of steady progression of the present moment is essentially this recursive Fourier transform back and forth between these two domains, the spatial domain and the frequency domain. There's a lot to say there, and that's really the essence of the paper. So I appreciate the question. And Cohen and Elitzur are two of my role models, so I really appreciate the comparison. I've referred to a lot of their work in my paper and in my own research. So really look up to them. And actually, they have a specific paper on whole top-down hierarchies. So that's something you can check out. But that's what I'm talking about here as a holism or a top-down hierarchy, and they've done work on that regard.
Okay, great. So here's more of a broad question. Can you expand on how free will is represented in this model?
Great question. So let's think about that. So free will, I mean, yes, what I'm discussing here with these paths and the slip and slide is like you don't have free will, right? You're on this path and you're sliding down the slip and slide and you can't get off until you get to the end. So when we're talking about light traveling from sun to earth, that's a great description because the light is a single trajectory from the sun to my eyes. If it hits a piece of dust and bounces in a different direction, or it hits a satellite instead, then a different map is associated with that trajectory, a different branch of the multiverse. And we can't know until it happens which branch we're on. and there's free will to put the satellite in place or not, or I have the free will to move my head or not. So I absolutely would say there's free will to choose between the branches of this multiverse. And those, and the way I see this unfolding at a broader level regarding synchronicity is that we reach specific choice points in our macroscopic life that lead us somewhere, and we're not completely constrained, but we're partially constrained. So if I if I apply for school and I enroll in school, now I'm on that trajectory. And this is sort of a metaphor for what we're talking about. You have free will to make that choice to apply to school and go to school. But then once you're on that trajectory, you're sort of on it for 4 years. And it's not exactly the same as the light leaving the sun and going to Earth, but it's a metaphor for how free will, we do have free will. And yet there's a sense in which we are constrained to paths. And there's kairos moments that are more opportune for change.
Okay, thank you very much for that answer. For a test of this theory, is there a way to falsify it? Have you thought of an experiment or of any way to test it?
Yeah, so I refer to a number of experiments that have already been done. We keep getting data that reinforces the relational model of quantum mechanics, which is essentially, if you're familiar with Wigner's friend experiment, thought experiment, Wigner suggested that if he goes into a room and measures an electron in a spin state, he'll get a result. And then his friend comes into the room, and what will she measure? Well, she'll also be able to measure the electron, but will she measure something that's already determined? Or will she be interacting with a superposition state for Wigner and the electron? In other words, is each measurement just a correlation, or is it some objective statement about the facts of the world? And there's an experiment by Proietti et al., Proietti, that has tested the Wigner's friend formalism. And I don't think anybody expected it to fail, but it was successful. And it supports, I wouldn't say it proves, but it's very consistent with the notion of relationality. So all of my suggestions have to do with relationality. My theory is fully committed to relationality, and that is testable according to Wigner's friend and some other ways of looking at it. The other paper I refer to is Schrodinger and Renner, who put a paper called Quantum Mechanics is Inconsistent with Itself, or something like that. And it just shows theoretically that there are some cases where you have to drop one of the assumptions we make about space and time. One of those assumptions that I think is the best one to drop is that there's an objective set of facts about the world for everybody. So that points to relationality once again.
Okay, super interesting. So here's another question. Does this have the same quality as the block universe, where everything that ever happened or will happen is part of a single holism map that simply exists? How does it relate to the branches of the multiverse?
Yeah, it's the same. What's specifically about the block universe that needs to be pointed out here is that the block universe in special relativity is usually thought of as a space-time block universe, where you've got a trajectory, like the block is like a piece of ice, and the cracks in the ice are the trajectories of the particles in space and time. That does not hold up here. What holds up is a frequency domain version of that. So the block is the frequency domain holographic pattern that encodes the motions, but does not resemble the motions. I think it's a useful way to put it. It encodes the motions, and it doesn't change. That block universe in frequency domain is unchanging, and it encodes a single branch of that tree, of that multiverse. And that is the block universe. It doesn't correspond to a single block universe in space and time. But I think that's clear. And this is one of the points I make in the paper, is that it's the frequency domain that has this frozen nature to it that encodes actual dynamics, space-time dynamics in it. It's a great question.
Okay. And what happened to the roads not taken in this formulation?
Well, that's a great question. That comes down to relationality. That's one of the big questions of a relational universe. When you talk about a physical world in the relational universe, you're always taking a perspective. So as I said, one of the conclusions from this formalism is that only events are real, are physical. And what that is saying is that if no one is around to observe an event, then you describe the event from the perspective of one electron hitting another electron. That's perfectly legitimate. And that event is a physical reality. But there's some way in which you have to take a perspective. So you take the perspective of that electron and describe the interaction from that perspective, or you take the perspective of a detector and describe the interaction from the perspective of that detector. The branches not taken are still just as mathematically present or real as they ever were, and all of that is accessible. Not accessible necessarily to me in my lifetime. I don't actually think, and I'm sure there's others here that might have shown differently or believe, experience, have different thoughts about this. I don't look for ways to travel back in time. I look for ways to understand time differently that includes the past, kind of like the dreaming of the Aboriginals. That I don't think we need to physically move to the past or future, but that all of that is still in the Fourier domain. It's omnipresent, right? When I transform into the frequency domain, the Fourier domain, I don't go somewhere. It's all right here. And so all that information of all the branches throughout all of history is all right here. And so it does point to some sense in which there's a non-locality in space and time that's very much just associated with the Fourier, the one-to-all nature of the Fourier transform. And I don't think it means we can space-time travel back in time, but we can access that information. So whether it's the Akashic records or any other of the things that would benefit from this model, I think it's consistent. And those, again, coming back to relational observation, there's a sense in which everything physical is described from the perspective of an observer. There's no such thing as the physical world without an observer. That's a postulate or a proposal that comes with relationality. And so the branches of the wave function that I didn't choose, there's no physical reality to them because I'm the observer and I'm not on those branches. So I think it gets rid of the extravagant notion of there's multiple versions of me out there. That doesn't really have any kind of meaningful content for me.
Yeah, of course. At least not for you as the observer per se.
Right, so, as the observer.
There's another question here. Well, there's a lot actually, but what is your view of super deterministic models, which seem to combine localism plus some kind of non-local correlation function?
That's interesting. I'm not sure I'm going to be able to answer that fully in a technical way. I'd like to know more about what the speaker is because I don't know as much as they do about the subject.
Okay.
Super deterministic means that there's, I think that it's overdetermined in some way, and so it has to do with free will. But I'm not sure. Love to know more.
Well, that may wait for the next emerging event that we'll have after this session have ended.
Great.
Does this relate to the demonstration of the observer effect of the wave-particle duality?
Yeah, let me think about how. So one of the basic examples I use in the paper, which is really simple mathematically, is a detector and a sine wave. You're detecting a sine wave. And the sine wave is, got its mathematical form, which is actually the Fourier transform mathematically of the detector's waveform. The detector I just call a delta function. And for those of you who are familiar, the delta function is just a totally localized function, just a 1 point. And so if you interact a delta function with a sine wave, you identify where that sine wave is. And so that's really the function of a detector. So can you read the question again so I make sure I answer it?
Sure. So if this relates to the demonstration of the observer effect or wave-particle duality of light.
Yeah, so I'm using that example to show that, when you, the wave, the whole frequency domain is waves, right? And the description that we get of the wave function, the waveform out of that is a distribution it's a wavy distribution in the frequency domain. It also corresponds to a wavy distribution in the spacetime domain. When we talk about the wave function and the wave particle duality, we're talking about the difference between wave propagation and detection. So a quantum system essentially propagates like a wave and is observed like a particle. And so when I do these calculations that are basically saying you're interacting a waveform with a detector that localizes it, I'm basically saying the method of observation is a Fourier and inverse Fourier transform pair. That's what observation is. And so it is absolutely a restatement of the observer effect. And if you understand Fourier transforms, you know that that is exactly where Heisenberg got the uncertainty principle from, because in the kernel of the Fourier transform is momentum times energy, and they have to have a certain minimal value. And that's why we can't have a completely localized position and a completely localized momentum because of the Fourier transform. So I'm saying that comes because observation is a Fourier and an inverse Fourier transform pair by definition.
Okay, super interesting. So what's the perspective, or your perspective, of the photon on the way from the sun to the earth during its journey? Does it know the final outcome, or live in all possible outcomes until it arrived and is or not seen?
Right. That's a great question. It's sort of slightly not formulated in an answerable way, because the questioner has said it really well, but what they're saying is that they're ascribing a reality to the photon's journey at every point. Unless you're the photon, you can't do that, because the path is described as a whole, and there's no reality to the nature of things between observations or between events, between interactions. So that's part of the nature of the wholeness of the path. We have to think about anything that we're observing existing, actually not existing in a definite form until we observe it. And this is what I call retroactive determination, where whether it's a photon or a satellite or the moon, in Einstein's case, you're talking about, does the moon really exist if I'm not there to see it? What's happening in this theory is that anything that happens to the moon is, you're not observing it. A meteor crashes on it. All of that is unobserved reality that is a superposition. And this is where superposition comes in, because the path or the reality as a whole exists in a whole timeline until you observe it. Then it's open to collapse a different way, or one way or the other, when you finally do observe it. So histories, in this sense, are flexible. The history of the photon is flexible depending on how you observe it. We can't describe a reality to the photon if we don't observe it.
Okay, so thank you very much, Sky. I will probably just end with one additional question, and then we can close this amazing presentation with Q&A. So in few words, if you can, what would you define as the observer?
That's a great question. Well, in relationality, you, like I said, you have to define the perspective from which you're viewing a system. Otherwise, you can't claim to have any kind of physical description of the system. So physicalness depends on picking an observer to be. So without the observer, I think of it in these two words. You can either have an objective, indefinite world. The multiverse is objective. It's like the whole reality, right? The whole cosmos, but it's not definite. Nobody's there observing it. It's a whole bunch of branches. And that's sort of, the God's view is all the possibilities. But that's an objective, indefinite world. If you want to have a definite world, it's by definition subjective. So that's where the observer comes in. There's no such thing as a combination of those two that I would call objective definite. Objective definite is forbidden by this model. So I think that answers the question.
But we can continue further on. But I thank you very much, Sky, for your excellent presentation. And I think our dear program chair has some announcements and other words that he may want to share with us.
Yeah, and we'll go on. If folks want to continue in this conversation, we'll talk more openly about the idea of synchronicity and your thoughts on it as well in the self-guided session after this.
So, Sky, I have to congratulate you. This is a very ambitious theory that you created here. And I mean, you made me understand Fourier transforms and holograms in a way I never have before. It's really great to see that you're able to express it simply enough to get through to people like me so I can make sense of it. It was really wonderful. and when you have such an all-encompassing theory that's this complete, you're going to get questions about everything under the sun and more, behind the sun and everywhere. Yeah. So we could probably go on for quite a while. I just want to thank you. It's really interesting to see a mathematical foundation for some of the things that we've been hearing about for so long. Thank you.